to the screen and sort of whiteboard. Can you see the whiteboard, both of you? Can you see?
Yes.
Yeah, so just as of now, just two of you, but let's hope people join later, because I want to sort of start wrapping up things, move a little bit faster so that we can cover a bit more ground. Sort of while people join, let me sort of state that what we did was we converted this basic, sort of quick revision. Really what we did was we converted this d to phi by d lambda square, this basic. I thought you people are familiar with this kind of differential equations, d phi by d lambda, right? Plus phi square lambda. Y is equal to 0. I hope you have come across this. This is for spherical coordinates. I did it for a sphere. That is why this term comes up. And that is why you have this transformation y is equal to lambda into phi, which gets rid of this term, you know. And we actually get it in the form d2y by d lambda square. Have you done this kind of transformations before? I'm sure you would have sort of heard about it. Y is equal to 0, which then is easy solvable. For example, I want you to go back and do it for, say, you know, this kind of, am I writing it right? Yeah. And of course, you know, the plane of symmetry is across this. So if this is the x-axis, you can do it for x is equal to 0 here to x is equal to 1 here and minus 1 here. And this will not appear at all. So I want you to go back and do the same thing for a different size. Usually the enzymes are in spherical pellets. So, you know, enzyme is all over the place. And obviously you realize that the surface area available for a porous enzyme is significantly larger than the surface area available only on the surface, because now each and every fine pore can be entrapped with enzymes. So obviously people prefer porous pellets, with the disadvantage, as I said, of internal mass transfer. But really, you can solve it for this geometry as well. Because I was using a spherical geometry, I got into this problem, and that is why I had to use this transformation to get it back to this shape. For this geometry, you will get this, and I want you to go back and derive this expression for yourself. And you will get the same expression, and you will get very similar profiles. So really what we did was that we solved this essential differential equation, which is rather obvious because this is plus here. So instead of the cos theta plus sine theta, it is now cos hyperbolic theta plus sine hyperbolic theta, and we managed to get your phi equal to what was it? A by lambda, some constant a by lambda, cos phi lambda plus b by lambda and sine hyperbolic phi lambda, right? And using the basic boundary condition that at lambda is equal to 0, which is at the midpoint, these values are finite, we managed to get rid of this expression because a is equal to 0. Because this is 0 here, so you know cost will be positive number, so you cannot get infinity, so a is equal to 0, so this term disappears. And then we found out b, and so we essentially, what was the final expression? We got Ca by Cas is equal to sine. No, wow, this is today, it has started giving trouble. So any questions till this point? Ca by Cas is equal to sine hyperbolic phi lambda upon lambda sine phi. This is what we got, right? With the boundary conditions and the substitution, finding out b and getting a equal to 0. B was 1 upon sine phi, so that is what. All of you remember this? And so I was able to, I'm just quickly summarizing this again. So I was able to sort of say that I can get plots like this of CA by CAS. And these plots, as you obviously realize, will be till the center of the point. R is equal to 0, R is equal to R is here. And this is, these are, as you move in this direction, this is of course a smaller phi. Because, diffusion not limiting. This is diffusion limiting, this is diffusion limiting, and that is diffusion not limiting. Diffusion limiting systems. And when there's less diffusion, the profile will be close to CAS. So as you move inside, you will have lower and lower concentrations. And now, given this fact, given this diffusion pattern, we can now say that because this is the diffusion pattern, let us say this is the diffusion pattern, obviously the reaction rate here will be higher, the reaction rate here will be higher, the reaction rate here will be slower and slower and slower. And here, as a matter of fact, there will be no reaction at all. And if this sort of went to 0, and you can see that this zone here for this plot is actually not being utilized at all. So that is what I was talking about in the previous class, that you can have a very small core of enzyme which is not utilized at all because it is a dead zone. The substrate cannot penetrate, so you cannot use very large beads. Why would you prefer large beads? Obviously, you prefer large beads because you don't want pressure drop. So you have to use small beads, especially because otherwise you will create a dead zone where the enzyme will be entrapped. For all practical purposes, these enzymes will not contribute to the conversion at all. They will not contribute to the conversion, and this plot tells you where this Ca value tends to go to 0 and your reaction rates are meaningless. And so this here, the velocity, the contribution of this part to the velocity of reaction converting A to B is actually negligible. And so that determines what is the size of the pores that you need to use. Is this argument clear? So this is essential summary. Now, really what we are interested in is finding out the efficiency of the reaction, which, as I told you in the last previous class, is the actual rate upon the rate in the absence of diffusion, the rate without diffusion, right? So rate without diffusion is very obvious. Rate without diffusion is nothing but Rx into 4/3 pi r cube, right? Because this is the volume. And so if you have a certain amount of loading, this is your reaction rate as far as, or if it was first order, Rx is nothing but Kca 4/3 pi r cube. Right? Now, what about the actual rate? Now, the actual rate is an integral of this rate, because here this is different rate, different rates. And so your Ca is now changing. It is not the constant all over the volume. So you have to actually integrate over this. Given this equation here, Ca is now has a profile. And so if you integrate this over the whole volume and take slices of it, and every slice has a different reaction rate because of the concentration drop, you can actually integrate and find out the reaction rate. Okay? Yes, no? Are you following what I'm trying to say? Hello? Have you guys left, or are you, all of you are listening, right? So I'm just sort of saying that some of you are there, I hope. So this you would have to integrate it over all these various, circular cross sections across, annular cross sections, and integrate it, and every time Ca is different, so the reaction rate is different. So it is not Kcas actually, which is the reaction rate without diffusion. It's Kcas 4/3 pi r cube, not Cas. But this now will be Ca, and Ca will be changing as R changes. But now I will do a trick. What is the trick I will do? I will now calculate the actual reaction rate, not by the tedious process of integrating over the whole process, but rather I will do the small trick of saying that, well, hold on, this substrate is diffusion here, right? Diffusing here. The Cas here is diffusing inside. And the rate of diffusion inside, given the certain profile that we have derived from these basic equations of diffusion equal to reaction, by definition matches the rate of reaction. So the rate of diffusion at the surface at lambda equal to 1 is indeed the rate of reaction, which will be equal to the integration of this amount. That is how we have derived this. So actually I can find out the actual rate by not integrating, which is more tedious, but actually differentiating this profile at lambda equal to 1. That's a better trick. That's an easier trick to do. So at this point here, I can look at the slope and different slopes will and multiply it by the diffusivity and actually determine the rate of reaction. So I can actually determine the flux. So this is the trick that I will do instead of integrating this, because this equation I derived from the fundamental material balance equations itself. Therefore, the material balance equation should match, and therefore I can simply say that my flux is equal to the rate of reaction. The flux is what? It is d whatever, right? D, the diffusivity, 4 pi r square, which is surface area, into dc by dr. dc by dr at r is equal to r. Are you following this argument? Yes. Which is of course also equal to, because we had this as this, which is this is equal to d. Can you tell me what is this? 4 pi r square into, because we have this as not dc by dr but d phi by d lambda into, what is it? What was the calculation? We did CAS upon R, right? Oh, sorry. Into CAS upon R. Right? That is this dc by dr being converted to, that is this dc by dr being converted to d phi by d lambda into CAS by R, which is equal to into CAS by R. So what R goes away, R here goes away, R goes away. So we get this equal to as d 4 pi, what is it? 4 pi R, right? CAS 4 pi r CS d phi by d lambda at lambda equal to 1 is also the actual reaction rate. You follow this argument? Right? So what is d phi by d lambda at lambda equal to 1? This I think you should derive. You know the CA by CAS. So भाई please इसको बताइए आप लोग क्या होगा? Okay. d phi by d lambda. d phi by d lambda is a simple differentiation at lambda equal to 1. Of course, they will substitute lambda equal to 1 later on. But tell me what is it? अभी हम लोगों ने derive किया था. भाई आपका यह है इक्वेशन, ये रहा. तो दिस इज u by v फॉर्म. मैं नीचे वाला लिख देता हूँ. लैम्डा साइन फाई u v स्क्वायर है ना, एंड देन लैम्डा साइन फाई. चलिए आप लोग बोलेंगे साइन h हाइपरबोलिक. आप लोग कुछ तो बोलिए भाई. हमारा डिफरेंशिएशन इंटीग्रेशन, मैं तो आजकल मॉलिक्यूलर बायोलॉजी करता हूँ, इनटू फाई cos, what is it? Phi lambda. Okay, ठीक है ना? Cos phi lambda into phi, because this is into phi. So v du by dv minus, sorry. Sorry, इसको extend कर देते हैं. This is this minus sin what? Hello, am I doing it right? Sin phi, this into, what is the derivative of the other one? I think this complete silence on your guy is very unnerving. Is it okay?
Yes, sir.
ये ठीक है ना? ये मैं इसको मिटा दूं. ये तो ऑब्वियस है. ये u by v फॉर्म का डिफरेंशिएशन तो बहुत कोई कठिन चीज नहीं है. ये तो मैंने भी शायद 10th 12th में पढ़ा था, है ना. आगे का मैथ्स मुझे नहीं आता है. ठीक है ना? सो दिस इज इक्वल टू, कैन यू प्लीज सिंप्लीफाई फॉर मी? 5 I'm trying to do this 5 cos phi. This square goes with this, right? 5 cos phi lambda. Is it all right? Okay. Upon only one lambda here. So this is 1 square lambda into sin phi. जहाँ साइन लिख रहा हूं मैं प्लीज रिमेंबर दैट साइन हाइपरबोलिक है ना इतना ज्यादा ओके माइनस ये 1 बाई लैम्डा स्क्वायर हो गया ये 1 बाई लैम्डा स्क्वायर हो गया तो साइन फाई ये कट जाएगा तो क्या होगा साइन क्या होगा लैम्डा फाई राइट लैम्डा फाई ऑफ कोर्स अपॉन साइन फाई नहीं ठीक कर रहा हूं हाँ this is sin phi one sin phi will go there one sin phi will get cut from this so sin is this all right did I okay do it correct hello हाँ ठीक किया cos phi I'm trying to do it on the board and you people should be contributing lambda equal to 1 चलिए सब्स्टिट्यूट तो कर दीजिए क्या होगा lambda equal to 1 में okay I'll wait I think I will wait rather than doing it myself. What is at lambda equal to? What is this expression equal to? I'll wait. I want some participation. This simple, algebra. I cannot have complete comprehensive silence here. But as it is, you have 5. I mean, in the next exam, I am going to sort of ask questions about actual derivations. Then, I will give you a triangular geometry or something, not the and ask you to solve it. Let us have some basic maths abilities here. Come on, Bhavya.
So it would come out as phi cos hyperbolic phi divided by sin hyperbolic phi minus 1.
So phi, what is it? Phi cot, right?
Yes, sir. Cot hyperbolic phi minus 1.
Not a big deal, right? So that's obvious. Phi cot phi, so is minus 1. So this is the expression that we have got, and so this is d phi by d lambda, and therefore what is m? What is the rate of reaction? What is efficiency? Now let us get this into. So we got this as, where was that expression? Oh, we rubbed it out. What was that expression this year? 4 pi r. 4 pi r CAS d. That was it, right? D. And now we have this d phi by dt. This is phi cot phi minus 1, right? Divided by this expression here, right? 4 by 3 pi r cube, right? K CAS for first order reaction, right? Is this all right? So the efficiency is 4 pi r CAS d. That was this reaction here, that into CAS by r. So this was 4 pi r CAS d upon this expression here. Now what is this equal to? Then now we'll rub this part out, and I hope you people are following this derivation, because I want you to be ready. So let us simplify this. So this is d phi by d lambda, and this is this. So and so we get phi equal to efficiency is equal to 4 pi r. So this is 3 goes up 3 by. Okay, now I hope you follow this. Phi square, I'll just jump. Phi cot phi minus 1. You know why I did this? Because what is phi equal to? Remember, for first order reaction, K r square by d. Remember this derivation? for first order reactions for phi? Do you remember what phi was? So I remember I derived this phi, no, this is phi square, sorry. Phi was R, I derived it in the last class. I derived this in the R root K by D for first order, because that Ca is n minus 1 was Ca is disappeared. So I can write this as, for first order reactions, I can write this as this, where phi square is equal to Kr square by D. All of you following this? So this is the last class. I had derived the value of for this what was it, phi, right? Okay with this so far, or is there some problem? Shall I halt here? Because remember, phi square was what? Okay, let me ask you, what was it? K CAS n minus 1 R square by D, right? Which becomes, for n equal to 1, for n equal to 1, it becomes KR square by D. So now notice K R square, this R here is R square, KR square, bring the D down, KR square by DE, right? Got it? So we have KR square by D, so we have essentially the efficiency as this expression here. Fine. And now, if I'm making mistakes, I think we are just going to go with it, because, you know, if you guys are just listening, then I have no problems. So as I said, phi square is also, I hope you realize this, it is a reaction rate. It is something like which I did, reaction rate upon diffusion rate. Diffusion rate, right? Phi square was also measured, which I sort of tried to demonstrate to you guys. And I mean, I'm not, because you're not sort of participating, I will sort of make a very peculiar remark that just like this, just like the Damkohler number, I will now sort of, this is where I will sort of jump, because derivations are not making much sense. If you, and anyway, you're not, guys are not. I hope you have heard of something called the Biot number. Have you heard of the Biot number, BI? Which is external diffusion upon internal diffusion, when both are present. And I'm going to sort of write the Biot number. I don't remember, what was it? Phi tan phi, I think. Yeah, I think phi tan phi upon dA. Phi is, of course, as you know, notice, a measure of the rate of reaction for internal diffusion, and dA is a measure of external diffusion. So depending on the Biot number, you can actually determine, this is also dimensionless quantity, whether internal diffusion is rate controlling or external diffusion is rate controlling when both are present. So sort of mention this very, very briefly, and it is not a very difficult derivation, but I leave it to you. Think about it. Phi tan phi upon dA is when both internal and external diffusion are happening. This is the pellet, and there is internal diffusion as well as there is a external diffusion. So there is substrate S bulk, and there is this surface at surface CAS, which I called, right? And there is a CA bulk, the CAS, and a CA profile. All three are present. And so you have a Biot number. And this is an important number to tell you whether the CA bulk to CAS is rate controlling or CAS down inside to CA is rate controlling. Let us sort of rub this out. But I sort of thought I would mention this because real life, of course, is a bit more complicated than the simplified versions that we are following. So let us get rid of this expression here. And we now have a efficiency for only internal mass transfer given by this expression here. Given by this expression here. 3 by phi square, phi cot phi minus 1. And of course, this we derived for first order equations, where I hope you realize that this phi square is equal to, of course, as I said, KCAS, this expression here, right, is now we are simplifying it as, what is it? So what is no, let us forget phi square, let us not forget. What is K? What is K? First order reaction constant. Now, what is it? Let me get down to the practical points, because we will say we are not solving questions here. V versus S. This is the plot. This is 0th order. This is V max. And this at half the velocity is Km. Right? So do you follow that K, is it equal to, for example, V max upon Km? Is it a good approximation? See, this is V max, this is Km. So I'm trying to sort of approximate this zone, this first order zone, where internal, because you see here this is 0th order. So if the substrate concentration goes from here to here, as far as I am concerned, my efficiency is not going to change. It is going to change when the substrate concentration goes from here to here, and it is a first order dependence. And so as CAS declines, as CA declines, my reaction rate changes, and that is why this efficiency here. So therefore, K is something like, you have to determine the K, and we will come back to this point later on. But really now let us concentrate on this expression here. And I hope you have calculators with you, but I am sort of going to use this basic argument that what happens when phi is very small and when phi is very large. So for phi being very small, what do you have? This is when phi is very small. What is efficiency? I just now talked about it, so you should be able to tell me what is efficiency? It is 1. There is no diffusion control. But for phi, so less than phi less than 1 or 2, but for phi greater than 2, we can use this approximation. We can write 3 by phi square. So this is the same thing. So phi is eta efficiency is equal to 3 by phi square. And we can safely write this as cot phi is almost gone, so we write phi minus 1. So we can approximate phi cot phi as simply phi when this is phi is greater than 2. And for phi values greater than 20, let us say, very, very highly diffusion controlled, and phi is very large, when we have phi values greater than, say, 20, okay, then we can simply write is equal to simply 3 by phi. That's it. This, because phi is very large, right? So if phi is very large and we have made this approximation, then phi minus 1 becomes equal to phi, and phi gets cancelled out, 3 by phi. So this is an approximation which is valid for phi greater than 20. So very highly diffusion controlled, we simply have an inverse 1 upon x kind of relationship with phi. So efficiency keeps on. That makes sense, right? So that makes sense. So really the plot of efficiency factor versus phi goes like this. बिल्कुल लास्ट में ऐसे जाएगा 3 by 5 है ना. So in the beginning it is equal to 1 for small values. In the intermediate zones greater than 2, it is given by this expression here. In the intermediate zones, here it is, I mean, low diffusion, and then intermediate zones, and then greater than 20, this is 20, this is 2, right? And then greater than 20, it is just 3 by 5. Are you following this plot? So phi versus efficiency, eta, is simply this expression when large values of eta are involved. So really now, so 3 by 5 is equal to how much? Now can we resubstitute it back again? So that the 3 by 5, what was phi equal to? Here. So can you substitute for efficiency 3 by 5? What is this expression equal to? Tell me. 3 by R come on, D or DE, whatever you want to call it, diffusivity by K, right? And so the reaction rate, so if phi is this, and you know that what is phi? Phi is actually actual reaction by reaction without diffusion. So what is the actual reaction rate? What is the actual rate? Phi into rate without diffusion, right? So 3 by R root dE by K, sorry, dE by K into what is the actual reaction rate? K1 into CAS, right? This is the actual reaction rate without diffusion, K1 into CAS, because K1 is the reaction rate and CAS is the concentration across the bulk. So if CAS was so the whole reaction would be K1 into CAS. So with this, therefore, this actual reaction rate, now the actual reaction rate, therefore, is equal to what? Can you simplify this expression here? So the actual reaction rate now becomes, so the reaction rate becomes equal to, for high levels of diffusion, 3 by R, and K cancel out, so we get root dK1 into, of course I'll put this in brackets, into CAS. This is a reaction rate with internal, when very high levels of internal diffusion are operating. So this is where internal diffusion is very dominant, and this where internal diffusion is dominant, the basic reaction rate is given by this expression here. Are all of you following this? Let me stop for a minute. And the algebra is not very complicated, I hope. So when phi is greater than 20, when you know there's tremendous amount of internal diffusion, you have a reaction rate given by this expression. Do you see the interesting thing about this reaction? What are the interesting things? It is dependent on diffusivity, obviously. It increases as a root of K. You understand the problem here? We have a, what was K? K is the reaction rate. It is dependent on the amount of enzyme loading that you have. Remember, Vmax is equal to K2 E naught. Don't forget all your enzyme kinetics. And so K, which is Vmax upon Kn, is actually a function of E naught. So when you double the amount of enzyme in a normal situation, when you double the amount of enzyme in a glass bead, you expect the reaction rate to double. But if you have diffusion control and you double the enzyme, your reaction rate will increase only root K times. Why? Because the more enzyme that you add, try to understand it in a very practical sense. The more enzyme that you add, the faster is the reaction rate, the more the diffusion control will become dominant. See, I have a profile inside. So this is the 0 to S, and I have some enzyme added inside. It's getting consumed. So my CAS profile is like this. CA profile versus radius. If I add more enzyme, my enzyme will get consumed faster. So my profile will tend to, this zone will tend to become, you know, completely starved, because the previous zones are eating up everything. And therefore, as you increase, say double the enzyme, the reaction rate will increase as a root of K, not as V. So these equations are important for actually solving problems. So if you have high diffusion control, my reaction rate increases as a root of K. And of course, it is completely inversely proportional to R. So you see why R has to be small. And it also increases as a root of diffusivity. So if you can increase diffusivity, but if you even increase diffusivity, it will increase as a root of D. So loading too much of enzyme in a shell which is highly diffusion controlled is not always a very great idea. Okay. So I mean, okay. Which brings me to the, I think we will do this in the practical on Monday, and actually, so let me pause here. I think, I do not know, is this clear? Am I going too fast? Am I going too slow? This is damn obvious. What is it? Some kind of statements from you guys. Earlier when I was teaching slowly, people, yeah, boli.
Sir, for phi greater than 20.
Sorry?
For phi greater than 20, sir.
Correct.
will that be a highly effective reaction or will that be a slow reaction?
Yes, that's a good question. Tell me, you don't answer the question. Just now I have drawn it here. What is when phi is greater than 20? What is the situation?
Efficiency is low.
Efficiency is low. And why is it low? What is the physical interpretation of phi greater than 20?
The diffusion is going faster than the rate.
Diffusion is going faster or diffusion is going slower? Diffusion rates are low.
Okay, sir.
Okay, so diffusion rates are low. That is why your efficiency is low. What is efficiency? Efficiency is rate, actual rate. What is efficiency? Efficiency is actual rate upon rate which you would have achieved without diffusion. If there was no diffusion, what? So a falling of efficiency means that the actual rate is tremendously impacted. So this low efficiency means the actual rate is much lower than the rate that you would have achieved without diffusion. So you really are interested in, and notice that this is becoming 3 by 5. So suppose this is equal to 25, or let us say 20, more than 20, 21. What is the efficiency? 1 by 7. So you are having 1/7 of the rate that you would have without diffusion. So which means really that you are losing out tremendously. So let me sort of ask the practical question. Okay, suppose I let us ask a practical question. How would you determine D? What kind of experiments would you do to determine D? Because that is what I thought I will do in the lab practicals. I mean, in a free enzyme, let us assume that the free enzyme, for the free enzyme, you know the Vmax and K. And as it gets immobilized, I mean, I suppose, Kshitij would have told you that the enzymes can, in the process of attachment, lose their Vmax and Km, because obviously attachment processes actually create structural hindrances and the Vmax and Km change, right? Have you heard this part? Did Kshitij tell you this? Or did you understand this problem? Hello?
Yes.
Yeah, so let us assume that you have a fantastic matrix and your Vmax and Km do not actually change. Okay, now I have, sorry, I will not rub out everything, otherwise you have a problem. You should not do this. Now let me actually is clear. Now all this is clear. I shall rub this part out. So now really I am saying the simple, I am giving you a simple problem to solve. Not simple, to sort of emphasize the concept. I have free enzyme, because all these equations make no sense unless you are able to apply them to meaningful real situations. The free enzyme has a certain Vmax and a certain Km. Right? And you have done that study, you have done the standard Michaelis-Menten kinetics and you have found out Vmax and K. Right? And now you sort of take a CSTR and put these free enzymes in the form of beads. Let me say that the diameter of the beads, D, dia of the beads is say 2 millimeter. Radius is 1 millimeter. And then obviously these beads will not escape, and I do this substrate concentrations here. I can put feed here, right? And depending on the feed rate, and F by V is D. Now please remember that dia D, diffusivity D, this is dilution rate D, right? So D, which many of you did, S naught minus S is equal to V max S upon Km plus S, right? And this is S out, this is S out, this is S out. And using these experiments at different dilution rates, I did, and I found out some Vmax value and some Km value. And unfortunately, these beads are just hold on for a minute. Okay, can you hear me? हेलो.
Yes, sir.
हाँ, तो अब मुझे बताइए आप लोग कि and there is some internal mass transfer present. First of all, tell me what will change because of internal mass transfer. Assume that the binding process or the entrapment process has not caused any real change in the free enzyme, but now we have internal mass transfer. Remember, in a CSTR, there is hardly any external mass transfer. External mass transfer is a problem of PFRs. External mass transfer is a problem in PFRs. In a CSTR, because there is a big large stirrer sitting inside and stirring the liquid, the film formation around beads is negligible, right? Because the beads are also moving. So this no slip condition, etc., doesn't happen in mixing. In a PFR, where the liquid is, I mean, I cannot draw it here. You understand what I mean. In a PFR, remember that because the Reynolds number is very small, which I told you about, wetted perimeter, diameter, etc., PFR, a packed bed, a densely packed bed, will have very low Reynolds number, and because of low Reynolds number, you will have the boundary conditions and the formation of a film, and therefore external mass transfer. So assume there is no external mass transfer and there is only internal mass transfer because of the beads. So the first question is, what would change? Vmax, Km, both, whether will they go up, will they go down, what will happen? Assuming that the binding process of the enzyme to the matrix has not changed the structure of the enzyme. बताइए क्या चेंज होगा? What would change in this kind of measurement? Suppose I would be able to do this with free enzymes or with beads which are so small that there is no internal diffusion. So I can do an actual measurement and I can do a real measurement, which is the actual rate in the presence of internal diffusion. What is the use of all this maths? Able to apply this. Please go ahead. So again, okay. So now 5 people left. That's good. Who is going to volunteer? Aishwarya? Snehadeep?
So I think VM will change.
VM will change. Why do you think VM will change?
Because for like
what is VM?
No, sir. I mean like K, the K value, the process, the rate of the reaction.
As I pointed out in the earlier case, VM never changes. Why does it not change? Because you can always overload the system with so much substrate that it becomes zeroth order. And when you have zeroth order reaction, then whether there is diffusion or not, the rate of reaction is independent of substrate concentration. You know the basic argument of zeroth order reaction, right? What is zeroth order reaction? The zeroth order reaction is one where the velocity is not a function of substrate. And the moment it is not a function of substrate, when velocity is a constant, it is a zeroth order reaction, then substrate concentration profiles don't impact on velocity. Do you follow this argument? So if the velocity, so VM never changes. But Kn will now become Km apparent. And I will want you, and this we will handle in the next class, I want you to think of what is it that if I get a certain Km apparent, how do I now use this to determine the say diffusivity, the dE. That is why I use the word diffusivity, given the diameter of the column. How would you use these equations to determine diffusivity if I know Km apparent? Tell me, let us have a guess. See, earlier, and shall I rub these things out? I mean, I hope you have some idea. I'll erase everything, let us say. Earlier, I had this whole argument for external mass transfer, which was very simple. In the external mass transfer, this was the rate and this was the rate with external mass transfer. And I could say that this is V, this is S. And so this is rate with external mass transfer, and this is the rate with no mass transfer. This is the real rate, the no mass transfer. And so if this is the Km, isn't it, half the maximum velocity, and this is Km apparent, then theoretically at this substrate concentration in the bulk, if this is the S bulk, you know, if this is S bulk, this is S at the interface, isn't it? So the Km minus Km apparent minus Km, this ratio is nothing but is the gradient across this field. At any point doesn't matter. This is the gradient. This is the gradient. And at each point, this gradient into K, into Ks actually, S1 minus S2 or S bulk minus S interface is equal to reaction rate, right? And this reaction rate is nothing but this V is equal to this V, right? Are you getting this point? So here notice the V is higher, but this driving force is also larger. Here notice V is smaller, but the driving force is also smaller. And if we look at these proportionalities, as V is falling, the driving force is also falling. But all of this can be used to determine Ks, the rate of diffusion. And from this, we can then find out the damped polar number. Right? So at different points, you can see this is for external diffusion. Now, what about internal diffusion? I again have a real plot given by the real enzyme without diffusion, and a plot that I get with internal diffusion. Notice all the cases, they all tend to maximum value. So with diffusion, and now this is internal diffusion. How would your formulation from your understanding change? How would your formulation change? So this was external diffusion. We had a certain method of solving it. So we did it by this mechanism, which I thought I had explained earlier. Now tell me, how would you solve it for internal diffusion? So please remember your basic equations. Your rate is equal to 3 by R root dE K1 CAS, right? And this rate is when phi is very, very large. Now, when is phi large in this case? Remember, this is V versus S. So as you grow lower and lower in S, the more will be the internal diffusion control, because it will tend to disappear faster and faster. So as your S, there is no S bulk here. It is now, this is not there. It is just the pore. And in this pore, the substrate is diffusing in. And this diffusion will become bigger problem when S at the interface, at the CAS here, is low. So this is equal to, and now this is what I'm trying to tell you, Vmax Km apparent, the Km apparent, into CAS. I don't know whether I'm making sense or not. But you have to think, what do you get when I take derivatives here? This is the derivative of dV by ds at S equal to 0 and dV by ds at S equal to 0. Do you now realize what this is? Rate is V. What is dV by ds? What is dV by ds? And notice that dV by ds at S equal to 0 is precisely when phi is greater than 20. Make sense? No? Yes? And can now, using these expressions, can you now, because you know your K1, this K1 here is actually Vm upon Km true. And this is Km apparent. And from these expressions, can you then derive this? If you know the radius of the pellet. If this is known. Let me stop here and leave you to think about this. Because as I said, you guys will get problems in the end. So, think about the questions and the derivations that we have done. I'm not going to do this in a very simple way. I want you people to, not absorb it in a passive sense. I just want you to think about what I'm doing here. Any questions? Did you follow what I said just now? Hello?
Yes, sir.
So, okay, think about it, solve a problem, try to understand what is going on, and let us stop here. Okay.
Thank you, sir.
Thank you.